Hi again, everyone. So today we have, in my opinion, a really fun day. This is probably going to be my favorite topic to teach out of, I would say, all of the sections that we're going to go through this semester, well, this summer. Um, so what we've done so far in this chapter, sections 3.1 and 3.2, we were defining the derivative. We were using the formal definition of the derivative, which was the limit as h approaches 0 of f of x plus h minus f of x all over h. And if you were to get a really crazy looking function or some crazy fraction or something like that, it would be a nightmare to use. But the cool thing is that we don't have to do that for any longer. Typically in math, we like to introduce the definitions first, and we like to do it the hard way first. And then the teachers or the professors go, actually, there's an easier way now. We can use the tricks. So now this is where I say, okay, there is an easier way. We can use the tricks. Now that you've practiced with some of the definitions, we can go ahead and use the tricks. Now, you may still get a question on an exam or a homework or something like that that says use the formal definition of the derivative and show your work like that. So I'm not saying that we need to forget about that. In fact, I'm saying the opposite. We still definitely need to remember the formal definition of the derivative and how to use it. But for some questions, it's just not feasible to use that. And so that's where we're going to be using a bunch of differentiation rules. So if there's ever going to be a section that you really should focus on and make sure you genuinely like memorize everything and understand everything, this is going to be the section. There's going to be a lot of rules that we're going to go through, and they are all just as important as the next. I will emphasize the ones that are a little bit more important, and I will give you my own little tips and tricks to help you memorize them. So hopefully it'll be a little bit easier, but everything in this section will come back very, very, very frequently throughout the rest of the semester. So if you have any struggles at all with this, I highly encourage you to spend some time making sure you understand it, because if you're not solid on your differentiation rules, it's going to make the rest of the sections and tests and everything like that very difficult. All right, so let's jump into it. First of all, we have this idea called the constant rule. I probably won't name this, use it by name, but we do have this idea that if you have some function f of x equals c for c some constant, then your derivative is 0. And what we have here is actually a little proof. So because of time, I've omitted most of the proofs for this semester. If you do like proofs and you like to see why things are the way they are, the textbook has some really nice proofs for pretty much everything, all of the nice little theorems. For the sake of time, I've had to omit most of the proofs, but this is a really easy proof that we could see. So for some constant c, you can't plug anything in. So f of x plus h is c and f of x is c. So when you plug it into the formal definition of the derivative, that's just c minus c, which is 0 over h, but 0 over anything is just 0. So that's the limit of 0, which is just 0. So this actually is a really easy way to prove that the limit of, or the derivative of constant is going to be 0. So this is going to be the formal definition. The derivative of c, so we remember d over dx means the derivative of, so the derivative of c is 0. I prefer this notation. So throughout today, we are going to see the notation both ways. So I'm going to show you the f of x, f prime of x way, but then we're also going to see the d over dx, so the derivative with respect to x of that thing equals what it equals. I want to show you both ways. You can choose which way you like. I'm going to highlight this one, though. I'll highlight the one that I suggest writing down. I think it's easier to view it like this, but if you like this, then by all means use that. All right, so this is me saying you don't have to write down everything. There's going to be a lot. So let's go ahead and try something. So find the derivatives of the following. So if we know the derivative is going to be just of a constant, then we know it's just 0. So these are very easy examples. So f prime of x is just 0, and g prime of x is just 0. It doesn't matter if it's positive or negative. It doesn't matter if you're taking the derivative of 5 million. The derivative is just going to be 0 because it's a constant. And a little bit more of like an intuitive reason why that is the way it is. If you remember from yesterday's lecture, we had this idea of, or maybe 2 lectures ago, I'm not sure exactly when, we had a graph and we wanted to graph the derivative of the derivative graph. And we had something that looked like this, and we said at a max or a min, the slope was 0, right? And so therefore, at our derivative graph, we had a 0. Well, a constant just looks like this throughout the entire graph. It's just a horizontal line. So the slope of a constant, because derivative is slope, the slope of the constant is 0 always because it's constant. Therefore, since slope is derivative, derivative is slope, the derivative of a constant is just 0 because that's the slope. So that's a little bit more of like an intuitive reason why this is what it is. All right. Now this, I'm going to say this is probably the most important rule of calculus. This is the power rule. I will be using the name for this quite often. Please know the power rule. Please don't get to the end of the semester where we don't know the power rule. This is so important. So this says, if you have some function, I'll get my highlighter, f of x equals x to the n, then the derivative f prime of x is n times x to the n minus 1. So what it's telling us to do is we multiply the exponent to the front of the term, then we subtract 1 from our exponent. And I know that this says let n be a positive integer. This is not the generalized power rule. We are not going to be looking at this. There is an extended power rule that I believe I might have later on. So this power rule will work for anything. You could have a fraction, you could have a decimal, it doesn't matter. For any n, so I'll rewrite this for any n. If f of x equals x to the n, then f prime of x is n x to the n minus 1. And this is the alternate way of looking at it. If you like the derivative with respect to x of x to the n, it's just the same exact thing, different notation. This is probably the most important rule of calculus. All right, let's try a little bit of practice with it. So let's find the derivatives of the following. First, we have x to the 11. So we remember that the derivative with respect to x of x to the n is n x to the n minus 1. So bring the exponent out front, and then you subtract 1 from the exponent. So that implies that the derivative of this function, instead of having to go through and use the limit definition, because imagine multiplying out x to the 11 times. That would be the worst thing ever. So instead of doing that, we now have like a really, really nice rule. So the derivative is take the exponent, multiply it out front, 11, keep the variable, subtract 1 from our exponent. So 11 minus 1 is 10. Therefore, our derivative is just 11x to the 10. All right, let's look at another one. If g of y is y cubed, then let's find the derivative. So g prime of y is take the exponent, bring it out front. So take the 3, bring it out front, keep our variable, and we subtract 1 from the exponent. 3 minus 1 is 2. All right, lastly, we have one that has a negative exponent. So what we're going to want to do is treat it the same way as we would anything else. It's a little bit, it's something that we need to put a little bit more attention into maybe, because when we're subtracting a negative, it gets more negative. So it doesn't go down in number, it goes up in number. So same thing, right? We just multiplied the negative 4 out front. So this is negative 4x, but then negative 4 minus 1 gets more negative, and so this is actually to the negative 5. I can do one more example. You may see something like 1 over x to the 7th, let's say. If you ever see anything like this, what we're going to want to do, I do believe that I have an example like this later on. What you want to do is you want to convert this to look like a regular old term that we would have. And so we remember the rule that says if you want to change the location of a base in a fraction, you negate the exponent. And so if I want to bring this into the numerator, all I have to do is negate the exponent. So to bring this up, I just negate the exponent. So this turns into x to the negative 7, technically over 1, but since we're dividing by 1, we don't have to write it. So therefore, the derivative of x to the negative 7 is take this, bring it out front. So this is negative 7x. and then minus 7, and then subtract 1 gets more negative, so that's to the negative 8. And if you wanted to rewrite this with a positive exponent for whatever reason, you can just go ahead and kind of go backwards with the rule. So this could be negative 7 over x to the 8th, like so. All right, now we have a lot of writing. This may seem kind of overwhelming. I'm going to highlight the parts that you need to know. It'll be a lot less overwhelming when you write down just these parts. So first of all, we have a sum rule that says if you have some function that's f plus g, where you have maybe two terms being added together, this doesn't necessarily need to be looking like two massive functions. F and g could just be two terms like x squared plus x cubed. So you have two terms being added together. You take the derivative. That is simply just taking the derivative of each term individually. This is kind of the more drawn out way of looking at it. I think it's a little bit harder to look at it like this, but if this makes sense to you, go for it. Look at it like this, whatever works. This is the way that I like to look at it. So if you have the derivative of something that's a bunch of things added, just take the derivative of everything separately. Same thing for a difference. If you have the difference of two things, you just take the derivative of everything and keep the subtraction there. Nothing changes there. We also have this constant multiple rule. So if you have something times your function, so maybe instead of like x to the 11th, like the example before, maybe you have 6x to the 11th. The derivative of that is just keeping the number out front and taking the derivative like normal. So if you have 6x to the 11th, you're still bringing the 11 down, but now you can multiply it by the 6th. And we'll do some examples that kind of explain this a little bit further. So we don't take the derivative of that constant. The constant just stays there. We take the derivative of whatever it is with the variable that we have. All right, so these are really the only things that you should know from this screen. That kind of eliminates a lot of the writing, and we can go ahead and try some examples now. All right, so first of all, this looks very similar to some of the things that we just took a look at. So compute the following derivatives. There are no numbers before it, so we don't need to necessarily consider the constant multiple rule. This is just the sum and difference rule. And the sum and difference rule just says take the derivative of everything and leave the sign in between. Therefore, f prime of x equals, so the derivative of x to the 6, we look at them all separately. Derivative of x to the 6, now using the power rule, take the 6, bring it out front. So that's 6x to the, subtract 1 from your exponent, so that's 5. Keep the plus, take the derivative of x to the 7th now. So x to the 7th, bring the 7 down, keep the x, subtract 1 from the exponent. 7 minus 1 is 6. Keep the minus. Now we're taking the derivative of x to the 8th. So let's bring the 8 down, keep the x, subtract 1 from the exponent. 8 minus 1 is 7. Therefore, the derivative is this function right here. All right, let's take a look at this next one. Now we do, in fact, have a number in front of our variable. Therefore, the derivative of our h function, instead of just taking the number and bringing it down, well, taking the number and bringing it down would be the same thing as multiplying by the constant out front. And so we're actually going to take the 2 and we're going to multiply it by the 4. And that's essentially what we're doing here, right? There's a 1 in front of all of these numbers. It's just implied. So we're multiplying the exponent here by the 1 in front. So the 1 times 6 is 6. It's the same thing here, just a little bit more difficult. So 2 times 4 gives us 8. X to the 2 minus 1 is just 1. So you don't have to write that if you don't want to. And then the derivative of 6, we remember that's the constant multiple, just the regular constant rule, sorry. When you take the derivative of a constant, it goes to 0. And so you don't have to write plus 0, you can just leave it blank. So the derivative of h prime of x is just x to, just 8x. All right, lastly, g of x gives us g prime of x equals, all right, I can break it down a little bit further just so we can see it a bit clearer. We can leave the 3 out front, bring the 5 down, so times 5x to the subtract 1 from the exponent, which is 4, minus 5 times, bring the exponent down, which is a 3x to the subtract 1 from the exponent, 2. Now x, that one looks a little bit more confusing. So let's go ahead and pull this off to the side. This is going to be the case for any time we see a single x with a 1 in the exponent. You could have a number before it as well. It doesn't matter. If you see an x and we're looking to take the derivative of this x, first we need to consider what the exponent of this is. The exponent of it is 1. If it's not written, it's a 1. So we'll treat this just like a regular power rule. Bring the 1 out front. Well, we don't have to write that because it's a 1. So that's 1x to the 1 minus 1, which is 0. Well, x to the 0, anything to the 0 is just 1. So this whole term just becomes 1. So what we actually have is anytime you have a single variable, that means like a variable to the first power, what its derivative will be is just the constant or the coefficient out front. So here it's a 1, therefore the derivative is 1. If this was, say, 4x, the derivative would just be 4. And so this is just plus 1. And then the derivative of this minus 1 here, since it's a constant, the derivative is just 0, so we don't have to write that. And so when we go ahead and simplify this, we can do 15x to the 4th minus 15x squared plus 1. That is the derivative of this function. Now we can kind of look at an application of this. So we're looking to find the equation of a tangent line, which is something that we've done before using this equation right here at 1. So before we would have used the limit as x goes to a of f of x minus f of a over x minus a. It would have been a lot longer. We had to watch out for a bunch of our variables, make sure we didn't do anything wrong. But now we don't have to do that because we have a really easy way of finding the derivative. Now we have rules. So what we have to do is we have to find the derivative like we did before. So f prime of x equals, but we have a rule that makes it a single step as opposed to, I don't know, 12. So we'll use our power rule, x squared, take the 2, bring it out front. So that's 2x to the 2 minus 1 is just 1. So now, as opposed to doing all the work that we did before, which was probably about 5 steps when we did it, we can just see that the derivative of x squared is 2x. Instead of doing all the work from the last lecture, the derivative is just 2x, and you can just say that. Minus 4x, so this is kind of what I was talking about before. Anytime you see that, the derivative is take the 1, bring it out front. So negative 4 times 1 is negative 4, but then x to the 1 minus 1 is x to the 0, but x to the 0 is just 1. So I'm not going to write that. The derivative of anything with just a single x is just to get rid of the x and leave the number out front. So 2x minus 4, the derivative of the 6 goes away because it's a constant. So the derivative of this function is 2x minus 4. Now we're looking to find the equation of the tangent line. Well, we need the slope. We remember derivative is slope. So if we're looking to find the derivative at x equals 1, we can find f prime at 1, which is just 2 times 1 minus 4, which is negative 2. So this just made everything so much simpler than we had it before. This is our m. All right, well, we know the equation of a line is y minus y1 equals mx minus x1. So we have to ask ourselves, do we have all the information we need? Well, we have an x, we have an m, we don't have a y. Well, we can very easily find the y. Now, we have to be careful to make sure that we're not using the f prime in place of the y. In order to find y, or y1 in this case, all we have to do is plug our x value into our original function. So we're looking for regular old f of 1, which is 1 squared minus 4 times 1 plus 6, which is 1 minus 4 plus 6. Well, 1 minus 4 is negative 3 plus 6 is positive 3. So this is like your y1, if you will. So our equation is y minus y1, which we said was 3, equals m, which was negative 2, x minus x1, which they told us was 1. And like I said, at least for my class, I don't need you to simplify that into y equals mx plus b. This is just okay. So this took what would have been way more steps and simplified it greatly. All right, now we get to some slightly more difficult rules. So a power rule is when you just have a single term. But what about if you have two things being multiplied together? Well, you can't just take the derivative in any way that you would expect. So we have to use what's called the product rule. So the product rule says if you have something times something else, then the derivative looks like this. So the derivative of f times g is f prime times g plus g prime times f. So what this means in my little trick is The derivative, so the product rule is if you consider this function the first function and this function the second function. The trick that I learned to memorize this is the derivative is the first times the derivative of the second plus the second times the derivative of the first. All right, this is kind of the trick. And when I'm doing it in my head, even to this day, I've been teaching this for so many years now. When I'm doing the product rule in my head, I say first times the derivative of the second plus second times the derivative of the first, where I just label the first function as the first and the second function as a second. All right. You can remember this notation if that helps, but I think that remembering it in this way is maybe a little bit easier. And I think that's exactly what this says here, just kind of in words. All right, so let's try an example. Now we have more of an applied example with numbers. So given j of x is f times g, use the product rule to find j prime of 2. So this may look a little bit confusing at first, but it's actually not so bad once we get into it. So first of all, anytime we're doing anything in calculus, if you're stuck from the beginning, odds are you probably have to take the derivative. So even if you have no clue what to do, just take the derivative because you're probably going to get some points because it's probably going to be some form of a derivative that you're being asked for. So j prime of 2, the first thing that we need to do is just find j prime. You don't ever want to jump right into j prime of 2 or whatever the number is, you want to take the derivative first. So if j prime is f times g, then, or if just j is f times g, then j prime is first times the derivative of the second. So it's f of x times the derivative of the second, which is g prime of x, plus second, which is g of x times the derivative of the first, f prime of x. And mine might look a tiny bit different than what we saw on the slide before, but we can remember that multiplication is commutative, so we can say that f times g prime is the same as g prime times f, and addition is commutative as well. So we can switch these two terms and it's the same exact thing. Okay, so we know that this is the product rule. Now, if we're looking for j prime of 2, that means that j prime of 2 is just plugging 2 in everywhere we see an x. So that's f of 2, g prime of 2, plus g of 2, f prime of 2. So at first, when you're looking at this, you might be really confused. So this is where my little suggestion comes into play, where I say, if you don't know what to do, just do something. Because maybe you don't know what to do, but you say, okay, I recognize this is a product. So you take the product rule. And then you say, okay, well, I recognize that this means I have to plug something in. And then you plug it in. And then you say, hey, look, that's exactly what I'm given. And then you plug it in and you get the right answer. So sometimes it's just baby steps that get us to the right point. Equals, now we just plug in. F of 2 says it's 3, times g prime of 2 is 6, plus g of 2 is 1, times f prime of 2 is -4, and I'll put parentheses around that because that's negative. So 3 times 6 is 18. 1 times -4 is -4. 18 minus 4 will just give us 14. Therefore, j prime of 2 is 14. So it's not quite so bad when you just do it step by step. All right, now what about if you're not given a number or a bunch of lists, right? So you're given two functions. We're looking for j prime of 2 by applying the product rule. So there's actually a couple of ways that we can approach something like this. So sometimes you absolutely have to use the product rule and there's no way around it. We have not gotten to the functions where it would be absolutely necessary to use the product rule, and we haven't talked about the cases using like binomial functions like this, where you would need the product rule as well. So we haven't gotten to a lot of the cases where you would absolutely need to use this. So that being said, you don't necessarily need the product rule for this specific question. So we're going to go ahead and do it two ways. So I'm going to show you both ways. For questions like this, you would be able to decide which way works best for you unless it's specified, like use the product rule for this. Again, most likely for product rule questions, it will be very obvious that you cannot do it any other way. You will be given functions that it just doesn't work. You can't multiply them out in any type of way that would make sense to be able to do this. If this is raised to the 11th power, you're not going to want to multiply that out 11 times. All right. So check the results first by finding the product and then differentiating. So if you have something times itself, we can go ahead and just multiply this out. We can distribute it, FOIL it, whatever you want to call it. So we can go ahead and make this into just a bunch of terms being added together and use the power rule. Typically, that's what we would want to do for this case, just because it is a little bit easier. Now, for the sake of this lecture, since we haven't gotten to the more difficult things, we are going to use the product rule for this, even though maybe it is a little bit more drawn out, but it's just for practice. So we're going to do both ways. Given the j prime of x is this, again, every single time I do a question, I'm going to rewrite the actual definition of what it means to be a product or whatever it is going forward. So for j prime of x, I'm going to label this guy as my f. I'm going to label this guy as my g, and I'm going to omit the of x's just because it doesn't necessarily need that. So the product rule is first times the derivative of the second, so f times g prime, plus second, which is g, times the derivative of the first, f prime. So see, maybe the slogan comes a little bit more naturally. I think there's songs for everything too, if you really want to stuck in your head. So we can use the product rule on one side, and we will use the simple distribution on the other. So here's the product rule, and then here's j of x equals x squared plus 2 times 3x cubed minus 5x on the other. All right, let's go ahead and try this one first. So let's just go ahead and FOIL this before we do anything else. X squared times 3x cubed is 3x to the, and then we remember if we multiply two bases that are the same, we just add the exponent. So it's 2 plus 3, which is 5. X squared times the negative 5x is minus 5x to the third, plus 2 times 3x to the third is plus 6x to the third. And then 2 times a negative 5x is minus 10x. Now, the last thing is I see that I can combine these two terms, so I will go ahead and combine them. I get 3x to the fifth plus, so 6 minus 5 gives us plus 1, x cubed. I won't write the 1 because that's not necessary, minus 10x. Okay. And let me double check that. Boom, 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 boom. Okay, always important to check our work. Now we can go ahead, since we just have a string of terms listed out, we can go ahead and take the derivative just using our regular old product rule. So j prime of x equals the derivative of 3x to the fifth. Says take our exponent, multiply by the thing out front. So 3 times 5 is 15, x to the, subtract 1 from the exponent, 4. Keep the sign, take the exponent, bring it out front. That's 3x to the 2. And then since we just have a regular old x here, the derivative is just getting rid of the x, keeping the number, so minus 10. So this is what we should wind up with. Now, let's go ahead and try it using the product rule. What we can do is we can write down the derivatives first, and then we can plug it in, and it'll be a little bit easier for us. So first, f prime of x equals, well, if f is x squared plus 2, then f prime is 2x, because you bring the 2 down, subtract 1, that's 1, but then the derivative of a constant is 0. So this is just 2x. The derivative of g is, well, the derivative of 3x to the third is bring the 3 down, multiply it by 3. That's 9x to the 3 minus 2, or 3 minus 1 is 2. And the derivative of minus 5x is just minus 5. All right, let's go ahead and plug it in. So this is j prime of x equals f, which is just x squared plus 2, times g prime, which is 9x squared minus 5, plus g, which is 3x cubed minus 5x, times f prime, which is 2x, and I've kind of run out of space. So this is the derivative using the product rule. Now it looks slightly longer, it looks slightly more complicated. If we were to go ahead and distribute, we could go ahead and prove that this is the same either way. So if you'd like to check this answer, we should be able to confirm that this is the same as if we were to distribute in the beginning and then take the derivative after. If I were to ask you to use the product rule, you do not have to simplify. In fact, I don't want you to simplify. That just leaves room for error. So if I said use the product rule, find the derivative, this is an okay answer as long as you do it correctly. You just leave it like that, say I'm done, and you get full credits. Okay, now What if it's not multiplication? What if it's division? Sometimes you can't get rid of the division. Sometimes it's just like x plus 1 over x minus 5, and there's no way of simplifying it. Well, then we have something called the quotient rule. So now the most important things we have is a little recap. We have the constant rule, the power rule, and then we do have some difference in constant multiple, but we don't really care about those so much. So we've constant, power, product, and now we're adding quotient into the mix. So these are all the very, very important rules. And in terms of the formula that you should probably have in mind, for j of x is some f over some g, where f and g are just some functions that are differentiable. Then the derivative is this guy right here, f prime g minus g prime f over g squared. Now, again, I said I have tricks for all of this. I think that this is really hard to memorize, especially for such a short period of time. This is how I was taught. If j of x is some function high over low, right? If this is some fraction, the numerator is higher than the denominator. That's just a silly way of thinking about it, but it works. If you have high over low, then j prime of x is low, and I'm going to denote the derivative as just a d here, d high. So the derivative of the high, the derivative of the numerator. So low d high minus high d low over low squared. All right, so low times the derivative of the high minus high times the derivative of the low over low squared, where this is high and this is low. And you can kind of sing it in your head, low d high minus high d low over low squared. And eventually it does actually catch on. Again, there's a song for it. Go ahead, get it stuck in your head. I know I did. I know that I've done that to my students and they've probably hated me for it, but that's okay. We're not in person for you to complain at me for getting things stuck in your head. So that's okay. So whichever way makes sense for you to memorize, that's okay. This is the way that sometimes is helpful when you're actually like doing it out. But if this way makes a little bit more sense because it's notational, go for it. So let's do some practice. All right, so use the quotient rule to find the derivative of this guy. So you notice there's absolutely no way that we can simplify this, which means that we have to use the quotient rule. In fact, at some point, we will be able to show that we could also use the product rule for this, but we don't yet have the tools to use the product rule for this. So we have to use the quotient rule. So I'll go ahead and use the notation that was given instead of my little trick. But my little trick will work once we get a little bit more comfortable with derivatives and maybe we don't have to write them down off to the side. So k of x equals f over g. So I'm going to define f of x as 5x squared. I'm going to define g of x as 4x plus 3. So what I'm going to do is I'm going to say, well, in that case, f prime of x equals, and then I'm going to take the derivative. So the derivative of 5x squared, take the 2, multiply by the 5, you get 10x. 2 minus 1 is just 1, so I'm not going to write that. So the derivative of 5x squared is 10x. All right, now let's take the derivative of g. G prime of x equals the derivative of 4x, since it's just to the 1, is just 4. The derivative of 3, well, that's a constant that goes to 0. So the derivative of 4x plus 3 is just 4. So now we have all of the information that we might possibly need, and we know that k prime of x is g f prime minus f g prime over g squared. This is probably the more simplified way. I think if you add the x's, it's maybe a little bit hard to remember. So this is the more simplified way of looking at it. We can just plug right into the formula once we have all of the information written down. So k prime of x equals g, which we said was 4x plus 3. And this is where parentheses are your best friend. Very, very important. Times f prime, which is 10x, minus f, general f, which is 5x squared, times g prime, which was just 4, over, and then in your denominator, you always, always, always need parentheses. So your whole denominator, 4x plus 3, all squared. And again, don't simplify this unless, like the numerator, if you want to multiply the 5 and the 4 together, you can, but that's like absolutely not necessary. This is a completely appropriate answer. And in fact, that's the answer I expect you to give me. Once you go ahead and write it all down, I just want to see that you know how to do calculus. If you can do pre-calc, well, I assume that you probably can do pre-calc because you're in calculus. All right. So this is how we do the quotient rule. All right. Let's go ahead and try another one because I know that this is a slightly trickier topic. So again, for h, we'll say h prime of x is, if we're given that h of x is f over g, then we can say that h prime of x is g f prime minus f g prime over g squared. So we'll define f of x as our numerator, which is 3x plus 1, and we'll define g of x as our denominator, which is 4x minus 3. So let's find the derivatives. So this implies, again, the double arrow means implies, or I guess it's a single arrow with two lines, how I draw a double arrow would have the arrow on the other side. So this implies that f prime of x equals, well, the derivative of 3x, since it's just a regular old x to the 1, multiply the 1 by the 3, you get 3, but then 1 minus 1 is 0, x to the 0 is just 1. So this is just 3. The derivative of 1 is 0 because it's a constant. So the derivative of 3x plus 1 is just 3. Now for the derivative of g, we have the same type of situation that we had before. 4x minus 3, well, the derivative of 4x is just 4, and the derivative of minus 3 is just 0 because it's a constant. So now we can plug right into our formula, and we can say h prime of x equals g, which we defined as 4x minus 3, times f prime, which is just 3, minus f, which we defined as 3x plus 1, times g prime, which we said was just 4, over our entire denominator, which is 4x minus 3, quantity squared. And again, this is just your answer. We are not going to simplify that. All right, now we're going to use the extended power rule that I mentioned before. So that's for any value for our exponent, not just an integer, and the constant multiple rule to find the derivative of this. So I'm going to rewrite it over here. F of x equals 6 over x squared. So there's a couple ways that you could do this. This specifies using the power rule and the constant multiple rule. So there's actually two ways you could do this. First way is if you wanted to use the quotient rule on this, you could. The quotient rule would work perfectly. It would just be way longer. But if one side of your fraction is just a single number and the other side of your fraction is a variable, then what you can do is you can bring that variable up into your numerator and just use the power rule. So what we have to do is we have to rewrite this first, kind of how we mentioned before. So I know in order to bring a variable from one side of the fraction to the other, I need to negate the exponent. So I want to keep the 6 because the 6 will just stay there. I want to bring this up to the exponent, to the numerator, so I'll negate my exponent. So this goes from an x to the positive 2 to x to the negative 2. Well, now we want to find the derivative of this. So f prime of x is just using our regular old power rule. So take our exponent, multiply by the number out front. 6 times minus 2 is minus 12x. And then we subtract 1 from the exponent. And again, we're careful because when you subtract from a negative number, it gets more negative, not positive. So minus 2 minus 1 is negative 3. And again, if you wanted to rewrite this as a fraction, you could bring this term back down into your denominator. Careful not to bring the 12 because these are just being multiplied. They're not exactly the same term. They're not stuck together by anything other than multiplication. So if you wanted to bring this down into your denominator, say you use the product rule and you wanted to, the quotient rule, you wanted to check, you could go ahead and bring this into your denominator by negating the exponent. Negating a negative turns it positive. So you'd get negative 12 over x to the positive 3. And if you were to simplify your quotient rule, this is the answer that you would get. It's just like so many less steps. So I suggest doing it this way. All right. Now let's try a problem that will be slightly more complicated. So sometimes we're going to have some problems that require multiple steps. So it's not just going to be a straightforward product rule, straightforward quotient rule. Maybe we're going to have a quotient and a product at the same time. And especially once we get to, I believe, the next lecture or the one after that, we're going to have maybe 3 or 4 rules going at the same time. And so we need to make sure that we're practicing implementing multiple rules at once. So this is obviously a quotient. There's no way of simplifying this. So we can go ahead and just set up our quotient rule before anything else. And we'll notice within our quotient rule that we will need to use a product rule. So for h of x equals f over g. We know the h prime of x is g f prime minus f g prime over g squared. So we can say let f of x be the numerator, which is 2x cubed times k of x. Now this may look a little bit funny. K of x is just some function. So now we're getting a little bit more abstract with it. We have to use our knowledge of just how functions work to be able to solve this problem. And g of x is just the denominator, which is 3x plus 2. Okay, now this is the tricky part, because f prime of x is the derivative of 2x cubed times k of x. And this is kind of what I mentioned before when I said that there are kind of few examples that we will see right now. That's a product rule where you can't make it nice. And this is actually one of them. There's no way of combining 2x to the third and k of x when we have no clue what k of x actually is. So we do need to use the product rule on this because this is a product between 2x cubed and k of x. So what we'll have to do is now use the product rule to get the derivative of our numerator. If you'd like to write it down separately, I suggest not using f and g again, because if you use f and g for your numerator, it gets a little bit confusing. Well, are we using f and g for the product or for the quotient? So you could probably call it two different things. You could call it u and v, maybe, or a and b, whatever you want that's not f and g. So we need f prime of x, but we don't have that. So let's go ahead and use our product rule on the numerator. So let's set it up. I will use u and v maybe. So let's call u of x the first part, which is 2x cubed, and let's call v of x k of x. Now this looks a little bit funny. This is just the second part. So it's like first times second. This tells us that the derivative of u is 3 times 2, which is 6x to the subtract 1, 2. And the derivative of v is, well, again, we don't know what the function k is. So the derivative of k is simply k prime of x, which tells us, I'll bring this down here, that f prime of x is, well, the product rule, I'll rewrite it up here, is first times the derivative of the second times second time, first times the derivative of the second plus second times the derivative of the first. In terms of u and v, let me write it like that. So in terms of u and v, you can say u times v prime plus v times u prime, maybe. So we could plug right into this. So u is 2x to the third times v prime, which is k prime of x, plus v, which is k of x, times u prime, which we said was 6x squared. So now this is our f prime. Now we can go ahead and find g prime of x. This one's easy. 3x plus 2, the derivative of 3x is just 3. The derivative of 2 is 0. So the derivative of g is just 3. Now we can go ahead and plug back into our general quotient rule, knowing that this is f prime. We had to use product rule for that. We have h prime of x equals g, which is 3x plus 2 times f prime. So I'm going to use a bracket to denote this. You can use a double set of parentheses if you want. A bracket is just a substitution for parentheses. Because we have a plus in here, we have a lot of parentheses going on. I don't want like 12 million parentheses, so I'm just going to do that. So we have 2x cubed k prime of x plus k of x times 6x squared. All right, that's just the first part. Now we're subtracting. Let me get rid of, sorry. I want to get rid of this little marking here. That's not supposed to be there. Minus f, which is just my numerator. So that's 2x cubed times k of x. I'll put parentheses around that whole thing, times g prime, which is just 3, all over the denominator squared. So that's 3x plus 2 quantity squared. And that is our answer. It looks kind of crazy. It looks kind of funky. That is just the answer because we don't actually know what k of x is. All right. Now we're going to look at something that we're going to come back to later on this semester. So this is a very important idea. So determine which of the values for x has a horizontal tangent line. So this is something that I've mentioned a couple of times. So what does it mean to have a horizontal tangent line? Well, if I have a function, we'll go back to this guy here, and I want to look at this here, the tangent line here and the tangent line here, well, I can't draw, but that should be tangent and it should be horizontal, right? So these two tangent lines are horizontal. We know that if this is some function f of x, we know that the derivative is the slope. So at these two spots, the slope is 0. So here f prime of x equals 0, and here f prime of x equals 0. So if we're looking for all values of x for which this has a horizontal tangent, what we want to do is we want to take the derivative of this function and then set it equal to 0, like we see here. So this is just kind of the visual representation of why it is that we need to do what we have to do. And what that is, again, is derivative of the function, set it equal to 0, and then we need to solve to find values of x. This is going to come back when we talk about intervals of increasing and decreasing, maxes and mins, and then we're going to talk about a further concept called concavity, which is just more or less how a function looks. All right, so let's go ahead and do that. F prime of x, f prime of x equals the derivative of x cubed is 3x squared. The derivative of minus 7x is 2 times minus 7 is minus 14x. 2 minus 1 is just 1, so I won't write that. The derivative of 8x is plus 8 because the x will go away. And the derivative of 1 is 0 because the derivative of a constant is 0, so I won't write that. So here, right here is our derivative function. Now we need to find the values of x that this has a horizontal tangent, which means that this has to be equal to 0. Now I need to go ahead and find values that make this true. What I recognize is that this is in fact a quadratic function. So if I can recognize that this is a quadratic function, I can take one of a couple different steps to actually solve to find the values. I might suggest the quadratic formula. So let's use it. X equals negative b plus or minus the square root of b squared minus 4ac all over 2a. Because I don't necessarily know if these values are going to be whole numbers, nice integers, or if it's going to be some weird looking square root. And a little reminder, this is a, this is b, and this is c, including the signs before them. So negative b is negative 14, which is a positive 14, plus or minus the square root of negative 14 squared minus 4 times a, which is 3, times c, which is 8, all over 2 times a, which is 3. And let's go ahead and get these values now. So I'm going to break out my handy dandy calculator. So this is negative 14 plus or minus the square root of 14 squared is 196 minus 4 times 3 is 12. 12 times 8 is 96 over 6. Now you might be inclined to say, well, 14 and 6 have something in common. Let's cancel out a 2. Be careful because we don't have any values in front of this term here, so we can't do that. So we're going to wait to cancel anything out or adjust anything until after we separate the plus and the minus completely. So this is negative 14 plus or minus, well, 196 minus 96, that's easy. That's the square root of 100 over 6, which, well, square root of 100, that's nice too. That's negative 14 plus or minus 10 over 6. And now that we have just some nice numbers, we can go ahead and separate it out into the plus side and the minus side. So x equals negative 14 plus 10 over 6, and x equals negative 14 minus 10 over 6. And we can find that. So negative 14 plus 10 is negative 4 over 6, which is negative 2/3. And this is why we wouldn't want to try to factor that by finding numbers that like multiply to whatever, because if you can think of negative 2/3, that's, you know, it gets to be a lot if you don't just use the quadratic formula. Negative 14 minus 10 is going to be negative 24. I don't know where I got an 8 from. All right, negative 24 over 6. And 24 over 6 is going to just be a positive, is going to be a 4, but we have a negative sign, so we bring that over, so that's negative 4. So determine which x values that have a horizontal tangent. That'll be x equals -2/3 and x equals -4. All right, last question of the day. I know this video is a little bit longer than normal, and again, that's because this is probably the most important topic out of any of them. So I apologize if this video is a bit longer, but it's longer because we just needed to do a little bit more practice in all of the types of questions that we have. All right. Last question, and this is an applications question. So this is thinking back to what we talked about in the last video of how velocity relates to a position function. We remember that s of t is a position. So anytime we're given an s of t, that is just the position function. And we remember that the velocity function is the derivative of the position function. So derivative of position function. So if we're looking to find the initial velocity, well, initial implies that this occurs at time 0. So what we need to do is we need to find the velocity function, which is the derivative of the position function, and then we'll plug in 0 afterwards. So we're looking for v of 0, which is the same thing as s prime of 0. All right, so let's find s prime of t, which is the same as v of t. Well, this is a quotient, which means that we're going to use the quotient rule. We know the quotient rule says if s of t is f over g, then s prime of t is g f prime minus f g prime over g squared. So we can go ahead and write out what each function is going to be and the derivatives. So we'll call f of x the numerator, or sorry, it'll be f of t in this case. Most of the time when we're working with real world examples, we like to use t as our variable just because we deal with time a lot. So f of t will just be t, and g of t will be t squared plus 1, which implies that f prime of t is the derivative of t to the 1 is just 1 t to the 0, but t to the 0 is 1, so the derivative is just 1. The derivative of g is, well, the derivative of t squared is 2t, and the derivative of 1 is 0, so we're not going to write that. So now we have all of our functions and our derivatives, and we can go ahead and plug into this. So again, s prime of t is v of t, so I'm just going to call it v of t equals, and we'll plug in what we have. So that's g, which is t squared plus 1, times f prime, which is just 1, so I didn't necessarily need to write that, minus f, which is t, times g prime, which is 2t, all over our denominator squared, which is t squared plus 1, quantity squared. All right, so this is the derivative. This is the velocity at any given time. It'll, of course, be positive time because time isn't negative, but we're looking for the initial velocity. So this implies that velocity at 0 equals, now let's just plug in 0. So this is 0, squared is just 0, so I don't need to write that. 0 plus 1 times 1 is just that thing, minus 0 times 2 times 0 over 0 plus 1 squared. Well, 0 plus 1 is 1, minus 0 is just 1, so the numerator is 1 over 1 squared is 1. 1 over 1 is just 1. And so the initial velocity is just 1, and they don't actually give us any units. So if they said like meters per second or feet per minute or whatever, we can put units at the end, but there's no units. So we can just say 1. All right, that's it for today. Sorry the video is a little bit longer, but these are the really, really important topics. So again, the most important things we covered today was the constant rule, the power rule, product rule, and the quotient rule. The next video, we're going to be covering another topic that's also really important, that's usually lumped in with these guys, but they take up so much time as it is that it has to be its own section. So make sure that you really understand how to use each one of these, do a bunch of practice, and if you have any questions, let me know.